This is about the Chapter 4 Plug and Chug problems. So problem number 36. Calculate the weight in newtons of a person who has a mass of 50 kilograms. This is, first off, the fact that they say 50 kilograms automatically means that we're dealing with a mass here. And it's just a straight plug and chug, as the section implies. So the weight of an object would be that mass, 50 kilograms, times g, little g. That's the acceleration due to gravity. And on Earth, the average is about 9.8 meters per second squared, but it does vary depending upon where you are on Earth. It is not a constant. So officially recognize this is not a conversion of mass into weight or kilograms into newtons. You cannot have an actual conversion if it's not always a set factor. So that's just 50 times 9.8 or 490 newtons. Small, number 39, a small apple weighs 1 newton. What is its mass in kilograms? What is its weight in pounds? So a small apple weighs about 1 newton. And so this time you're dealing with weight equals mg again, except this time you know what that is on the left-hand side of the equation. So 1 newton is equal to mass times g. Let's assume it takes place on Earth. So 1 newton equals mass times 9.8 meters per second squared. Divide both sides by 9.8 meters per second squared, and you get the math part is 1 divided by 9.8, which is roughly 0.1. It's going to be a little bit bigger than 0.1, and that will put it in kilograms. Now, the weight in pounds, and I think this is a place where in the solution, what Hewitt does is he takes the mass and does a conversion factor into pounds, and that's just wrong on so many levels, because you are making the assumption that that 1 newton is on Earth. So if you look in the back of the book, and I've got the book right here, you look in the back of the book, and there is a conversion from pounds into newtons. 1 pound is 4.448 newtons. That is a proper conversion factor. And so, therefore, if you have a 1 newton there, well, you set up a ratio. 1 pound is the 4.448 newtons as 1 newton, as x pounds is to 1 newton. And so you end up, well, numerically, a pound is bigger than a newton. So it's going to end up being 1 divided by 4.448, the number of pounds. Another way of looking at it is my weight's about 210 pounds, somewhere in there, 215. My weight in newtons is about 1,000 newtons. So just to give you an idea of the conversion there. Number 41, calculate the acceleration of a 2,000 kilogram single-engine airplane as it begins takeoff with an engine thrust of 500 newtons. And again, this is, plug and chug into Newton's second law, the fact that force is equal to mass times acceleration. The force is 500 newtons, the mass is 2,000 kilograms, and so 500 equals 2,000 times the acceleration. Probably the biggest mistake I see students make at this point is they divide the bigger number by the smaller number, and that's just not the case here. It's 500 divided by 2,000, which is 1/4 or 0.25. And they're looking for acceleration, so 0.25 meters per second squared. Number 43, consider a 40 kilogram block of cement that is pulled sideways with a net force of 200 newtons. And again, we have plug in the F equals to ma, or as he writes it, acceleration is force divided by mass. It's the same equation, just slightly different order. So if we consider a 40 kilogram block, now he doesn't say it explicitly, but the fact that it's kilograms tells you its mass. So the mass is 40 kilograms. The force is 200 newtons. That's the net force or total force. And so you'll end up doing 200 newtons divided by 40 kilograms. The math is 200 divided by 40, which is 5. And then you have newtons divided by kilograms, which is the same as meters per second squared, as we talked about in class and as is mentioned in problem 41. And that's it for the plug and chug from chapter 4.